Thank you. I'm happy to be there. This is Let LLMs Wonder, so how to engineer RL environments. I'm Stefano Fiorucci, AI and software engineer. I work at DeepSeek on the open source AI orchestration framework called Haystack, and I love tinkering with small language models, fine-tuning, and reinforcement learning. So today we are going to talk about reinforcement learning environments for language models evaluation and training. This has been a hot topic over the last year, and I find this exciting because these are actually engines to make language model agents improve. And also, startups working on this space are getting major funding and collaborating with big AI labs. If we look at recent technical report by DeepSeek and Minimax, we see that they used thousands of environments to make these models improve on challenging tasks and basically to scale intelligence. Don't worry if you know nothing about this topic. I hope that this talk can cover this. So, this is the agenda for this talk. We'll first introduce reinforcement learning and see how this maps to language models. I'll then explore together with you verifiers, an open source library to build environments as software artifacts. And then we'll apply reinforcement learning environments to make small language models play and learn tic-tac-toe. You can find all materials on GitHub. I created a small and free course about this topic. So let's start. In reinforcement learning, there are two main characters, the agent and the environment. The environment is the world where the agent lives. And at each step, the agent takes an action, and the environment modifies its state in response to this action, and also provides the agent with a reward, a number indicating how good or bad the state is. So the goal for the agent is to maximize its cumulative rewards over time, and to do so, it has to balance exploration, so trying new strategies, and exploitation, so using strategies known to work. Basically, it learns through its experience over time. And when we look at the sequence of actions, states, and rewards, we call this trajectory or rollout. A language model, as you know, is a statistical model that, given some text called prompt, produces a text completion. And the classical LLM training is divided into three steps. The first one is pre-training, where the model learns how to produce text completion and on a huge corpus of web data generally. And the base model coming out from this phase is not usable right out of the box. So we perform supervised fine-tuning on conversational examples. And during this phase, the model learns to follow instructions and also learns new tasks. And then there's the third step of preference optimization, where using several techniques, the model is aligned with human preferences. Let's take a quick look at supervised fine-tuning data, because during this talk, we'll frequently compare this approach with new reinforcement learning-based techniques. So in supervised fine-tuning, we have pairs of prompt and responses, and during this kind of training, the model learns to imitate these examples. So once the model is trained, the text completion produced are close in distribution to the original training data. At some point, this approach started showing its limits. You might remember Ilya's talk at New Rips 2024. The idea is that this classical LLM training approach was no longer able to keep improving model abilities at the same rate. So we needed a new way to scale model intelligence. When OpenAI O1 series of model was released, they just said that they used reinforcement learning to make the models produce chain of thought. So in the text completion, a first part is the chain of thought or reasoning trace, and we then have a final answer. They also showed this plot where spending more time in reinforcement learning training, so more train time compute, or giving the model more time to think, so giving more test time compute, the performance on a challenging mathematical task was improving. But they did not express details on how they actually trained the model. Then DeepSeek R1 was released, and it contained a way in which you can possibly achieve the same result. First, they recognized that reasoning, so chain of thought, is important to make the model performance improve on certain tasks. But they also realized that teaching this via examples, so via supervised fine-tuning, is hard because it would require, especially for reasoning traces, long curated examples, and this is expensive to produce at scale. So they used another approach, reinforcement learning with verifiable rewards, which we'll see in a moment, and they also applied a new technique, a reinforcement learning technique called GRPO, which is simpler and lighter than previous techniques like PPO. So, in reinforcement learning with verifiable rewards, we ask the model a question, and the model produces a thinking trace and a final answer. This answer is then compared to the ground truth answer using a deterministic verifier, which can also be a very simple Python function. And this verifier produces a reward, which is then fed into a reinforcement learning optimization algorithm. So this paradigm is very different from supervised fine-tuning. First of all, because here the model just sees the question. The ground truth answer is only provided to the verifier. And doing this, the model can evolve its reasoning trace without examples, but can learn over time to produce the reasoning trace that leads to better answers. And it's also different from supervised fine-tuning because here the model is no longer limited by the quality of human examples. And this paradigm is also more general than it might seem, because you can apply to whatever task whose outcome can be automatically verified. So in this case, a matching answer, but also a won game, a passing test. And so we can finally map this reinforcement learning concept to language models. And so the agent is the language model, the action is its textual response, and the environment is whatever you need to evaluate and possibly train your model on a certain task. So data, harnesses, and scoring rules. As we know, the concept of agent is also expanding, and now language models can be given tools from a simple weather API to a terminal. But to make this more concrete, let's take our tic-tac-toe example. In this case, the agent is still the language model. The action is the produced text completion, including the specific move. And the environment is basically the game engine. So it takes care of prompting the model, making the game progress, so keeping track of the board status, producing the opponent response, and deciding when the game is over. You might have understood that I'm enthusiastic about this topic, but let's also use Andrei Karpathy's word. Reinforcement learning environments give the LLM an opportunity to actually interact, take action, see outcomes. This means you can hope to do a lot better than statistical expert imitation. Now it's time to see how to actually build this environments, while in supervised fine-tuning, basically the task can be represented by a static dataset. For reinforcement learning environments, we can see them as software artifacts. And I've explored verifiers, which is an open source library by Prime Intellect, to build these environments as software artifacts, both for evaluation and training. And they are Python packages, which can be installed and distributed. And this library contains several pre-built environments types you can use and inherit from. It contains utilities for parsing the textual response and also for defining rewards. And when it comes to inference, it abstracts inference, so works with whatever OpenAI compatible API, so also models hosted, for example, on OpenRouter, or open models served via VLLM. It provides async and parallel execution out of the box, so you don't need to implement these details. And it integrates nicely with several training libraries. But let's start taking a look at the simple verifiers environment. In this case, the task is to just reverse a paragraph of text. So here we can see the load environment function, which we can find in every verifier environment. And what happens here is that a dataset is loaded from Hugging Face, and here we map the text to reverse to the question field, and then we put in the answer the ground truth answer, which is the reversed text. We defined an XML parser because in the system prompt we indicate that we want our model to put the reversed text into reversed text XML tags. And we then define a reward function that compares the model response with the ground truth answer, and it computes the longest common subsequent ratio. Then this reward function is bundled into a rubric, and then our environment is done. But how this come into life? We can, for example, use this to run evaluation. We specify the environment name, we specify the model, that in this case is GPT-4.1 mini. We then specify that in this case we want 3 examples from the dataset, and each of them repeated for 3 rollouts, because due to model randomness we will have different results. So when we run this command, basically these examples are extracted from the dataset, a prompt is prepared for the model, and then we have the task executing. We get a response from the model. This is parsed, rewards are computed, and finally we get summary statistics. Let's now take a look at a bit more complex environment. In this case, we have more than one interaction between the model and the environment. And in fact, here state makes its first appearance, and state is basically a Python dictionary containing information we carry across all the rollout. In this case, the task is that we ask a mathematical question to the model response, and then we ask, are you sure? And we get the final response. So we also notice the env-response method, and this contains actually the response from the environment that in this case is fixed. So it's just a user message asking, are you sure? But in general, it can be defined dynamically based on state. Another interesting thing to see is the VF stop decorator. This marks a method as a stopping condition. So when this this condition is evaluated at the beginning of each turn, and when it evaluates, when it returns true, the rollouts terminate. Another kind of environment is the tool environment, which is basically a multi-turn environment with tools put into the mix. In these simple examples, tools are just Python function. And in this case, the model can prepare tool calls, and then the tool calls are executed. And the standard stopping condition for this kind of environment is when the model returns a response that does not contain tools invocations. And this is pretty basic, but I also recommend taking a look at the wiki search environment, which is a bit more complex and realistic. Verifiers provides you with several other kind of ready-made environments. For example, the MCP toolenv, when you want to load tools from a model context protocol servers, but it also plays nicely with several other reinforcement learning environments libraries. So you can, for example, import an environment created with OpenEnv and use it in verifiers. To end our quick overview on verifiers, I recommend checking out the Environments Hub. This is a community place where to publish and share environments. This aim to fight the environment fragmentation. In research, is especially common that people release environments on GitHub tied to a specific training task, so then it's harder to reuse them. But also in a world where frontier models are constantly trained on reinforcement learning environments we don't know of, this is also an effort to do a democratization of this domain. But apart from that, it's also fun to see what people build with environments. And now, finally, I want to guide you through my small experiment. In this case, I took a small model and used a reinforcement learning environment to make it play tic-tac-toe. So why? This is a simple task, apparently, because it's a simple game with a deterministic solution, a small state space. Still, language models struggle. Also, some frontier models are not perfect tic-tac-toe players. And also, this requires multi-turn interactions between the model and the game engine. And since also the opponent response may vary, it's a kind of task that is a bit hard to capture well with a static dataset, while a dynamic software artifact like a reinforcement learning environment seems more adapted. So, let's start with an initial implementation. We make a few simplifying assumptions at the beginning. So our model will always place as X and always place first. It has to output a move which is an integer between 0 and 8. And for the moment, the opponent will always play randomly. So in this first part of the code, we see in load environment that we basically create messages to prompt the model, showing to the model the initial empty board and asking for a move. And here it's also interesting to see setup state. Here we define the initial state with an empty board and winner set to none. And then this state is updated over the rollouts. But then in env response, we have the actual game engine. Here we parse the answer from the model. We validate it. If the move is invalid, for the moment we stop the game with a loss. This is a decision I revisited later. Then, if the move is valid, we apply it to the board and we check for a win or for a draw. And if the game is not finished, we select a random move for the opponent and we do the same check for a win or a draw. And finally, if the game is not yet finished, we prompt the model again with the new board status and asking for a move. Important, let's take a look at reward functions we define. A very simple reward function at the end of the game. So 1 if the model won, 0.5 for a draw, and 0 for a loss. And then we also expect our model to respond with a move inside the XML move tags. So we also apply a format reward function. And this is just the initial implementation. I then iterated over this while trying both to evaluate models and to train models. And so I made some improvements. First of all, we want to vary who start the game. Sometimes the model, sometimes the environment. Then playing against a random opponent is not realistic. So we create an optimal opponent using the minimax algorithm, but also playing always against an optimal opponent is not great for our model, especially if our model is a small one, because against an optimal opponent it would always lose, and so we would not get training signal. So we instead decide to use an optimal opponent with a probability of making a random move. And we parameterize our environment with a minimum random move probability and a maximum random move probability. So if both they are set to 0, we have purely optimal opponents. If both are set to 1, we have purely random opponents. So by deciding on these parameters, we can vary the opponent's skills. As we have seen, another important aspect is to make our model produce a chain of thought, a thinking trace. So we also ask our model to produce this, and we enforce this in the format reward function. So we expect to have this think part in the response. And a quick note about invalid moves. When experiment with small models, especially at the beginning, the models do a lot of invalid moves, and terminating the game with a loss is harsh, and also in this case we risk not giving the model signal to learn. So I instead decided to make the model retry up to a certain number of turns, but if the game contains invalid moves, I also apply a flat penalty of minus 0.1. This is basically a negative reward. Then a quick note about noise. Reinforcement learning is unstable, and so we will use group-based reinforcement learning, meaning that inside a group of, let's say, 8 games, we want to reinforce the best games. So it's important to reduce noise so that the best rewards come from how our model played, not from chance. So I reduce noise inside groups, but I also try to reduce noise across batches. A batch is basically the number, contains basically the number of games before each model weights update. But to look at this, I recommend checking out the full code in the repo. So let's finally try to use this environment, first of all, for evaluating existing models. So I evaluated the GPT-5 Mini, and we see that it's a good tic-tac-toe player. It follows format perfectly, but it's not perfect because against an optimal opponent, it loses almost 25% of the time. Then I focused on my small model. I used LFM2 by Liquid AI, and this struggles a lot, especially with format, and is not a good tic-tac-toe player. It sometimes wins against a random player, but against an optimal opponent, it loses almost 9% of the time. So, since I want to make this model better, a good idea could be, before applying reinforcement learning, to do a quick supervised fine-tuning warm-up to just make our model learn format. This is a standard approach to apply some supervised fine-tuning warm-up before passing to reinforcement learning. So we now need supervised fine-tuning data and how to produce them. Our reinforcement learning environment is secretly a machine to produce supervised fine-tuning data. So if we run this evaluation command using GPT-5 Mini and we save the output to Hugging Face, we get a supervised fine-tuning data, so with the prompt and the completion. This is usable for training, and using the PrimerL training library, I spin up a quick supervised fine-tuning warm-up. This took like 15 minutes. Yeah, the loss function seems to look good, but let's evaluate the supervised fine-tuning model. And in this case, we see that it follows format almost perfectly, and it, as a side effect, also its game performance improved, but there's still significant work to do, and so we can finally apply reinforcement learning. But first, a quick recap of GRPO, the algorithm we use. The main idea behind the GRPO is that we make the model produce several rollouts, several games, a group of them, and we reinforce the best rollouts inside the group. So we have this interaction between the language model and the environment. We start from the same initial board, the same opponent skill, and due to variability in across 8 games, we could have different results, and we compute the rewards, so +1 for a win and 0 for a loss. We then compute the average of rewards across the group. This is the baseline. And then we compare each rollout with the baseline. And this phase is called advantage computation. And we then reinforce the best performing rollouts. So this is the idea. Let's see this in practice. In this case, I'm using another training library, which is a small trainer inside the verifier library. Lot of parameters in the repo. I recommend how to set them, but I would like you to focus on 2 main aspects. Here we are setting a minimum random move probability, or the random move probability is ranging from 20% to 70%. This means we have no perfectly optimal players and no purely random players. So this is a good playground for our model to learn both attack and defense. And as we generally do in GRPO, we use one GPU for inference and another one for training. And another important point is the batch size. In this case, I used 256. It's important to have this value not very low, because this is the number of games before we apply a model update. So if, for example, we decide to have 16, this means that the model is learning from just 16 games. And it may just learn strategies that work for this specific small number of games. So I have found that batch size is very important and should be high. But yeah, with this configuration, we can spin up training, and we can take a look at our loss curves, and we see that the reward, the general total reward, improved over time. But let's take a look at real evaluation numbers. Yeah, and we see that our model actually improved both against a random opponent and also against an optimal opponent, but it's not perfect. It loses 15% of the time against an optimal opponent. And inspecting rollouts, I have seen that our models tend to fall into fork traps. So I wondered if using the same reinforcement learning environment, I can make my model better. And so I tried, and I applied two main changes. One is about the random move probability. So in these cases, it ranges from 0 to 25%. This means the opponents are stronger than before, but not poorly optimal. I also tried purely optimal, but my model became overly defensive and was no longer able to exploit opponents' errors. And another change I made is temperature. I realized that some suboptimal strategies were fully baked into my model, so I increased temperature to make my model explore more. This is something to do with care, because if temperature is too high, the model can start producing garbage. Let's take a look at the plots, and yeah, they are interesting. In particular, I find it interesting that initially our reward dropped and then started climbing again. And I interpret this like an initial phase where the model was trying random strategies. But let's finally evaluate the model. And yeah, we see that in this case, the results are very good. In particular, yeah, against an optimal opponent, it almost always draws, which is nice. But we can now also compare our model with GPT-5 Mini, which is the model we used also for the quick supervised fine-tuning warm-up. And against a random opponent, our model is now on par with GPT-5 Mini. But against an optimal opponent, yeah, our model managed to beat GPT-5 Mini. Of course, just in this specific task. So, I want to leave you with some thoughts. During this talk, we first introduced the reinforcement learning concept and see how they map to language models, and I especially introduce reinforcement learning with verifiable rewards and the concept of environments. We then gave a look at verifiers, open source library to build them, and yeah, then I showed you this experiment about tic-tac-toe and a very small model. Nowadays, reinforcement learning with verifiable rewards and reinforcement learning environments, they are part of the post-training LLM stack, and they are complementary to supervised fine-tuning. They did not replace supervised fine-tuning, but they are a part of it. And another quick thought is that if you can create a reinforcement learning environment that gives a signal to train on, you can also take a small language model and hope to make it beat proprietary model on a specific task you're interested about. For example, yeah, let's take this example. You might frequently call 2 or 3 tools, and you use a proprietary model, which is good at them. You can, if you are able to build an environment, you can take a small language model and try to improve it in the specific tooling of the tools you need. That said, thank you for your attention, and you can find all materials on GitHub, and I'm open to questions. Thank you.
Any questions?
Thank you. That was very interesting. I was wondering if you have evaluated if the model you have trained to do this task loses skill on others. Like, do you do performance testing on other tasks that this model was performing well before the fine-tuning? Have you noticed something like that?
No, in my case, I haven't tried, but I should. What I can say in general, but this is from literature, not from my task, is that reinforcement learning is generally a lot less aggressive than supervised fine-tuning, because it's on policy. And so, for example, in supervised fine-tuning, the risk of catastrophic forgetting after training it on several tasks is very concrete. On reinforcement learning, it seems that it moves the model less, so it's less likely. But no, in this case, I haven't tried, but good question.
Hello, thanks for your talk, first of all. I was curious to understand if there are differences between the playing with the knob of exploration and exploitation or playing with the temperature. Does it have the same outcome on then the model, or worse?
No, could you explain it a bit better?
So in reinforcement learning, we were talking, sometimes you explore something new, sometimes you exploit what you know it works. But then with the LLM model, you can also play with the temperature. So it kind of does something different. And I was wondering if the outcome is exactly the same, or if...
I'm probably... I don't know if I can answer, but in my case, I basically played with temperature because, by training a language model, I just have at that time I just had this knob to manipulate, and particularly my model at some point learned very specific and not good moves. So I initially haven't thought about temperature, but then I resorted to this because it was a way to increase exploration in my case. Yeah, but I don't have a more general answer.
Thank you.
So thank you. One last question, urgent question. Okay, yes?
Yeah, it's a quick one. Thank you for your talk. It was amazing. I was wondering, did you make it so that one model played another? Like GPT-5 Mini versus your trained model? Could you do that and try?
No. I should try also this, but haven't.
Okay. Thank you, Stefano.